All right, so we'll get going. Today's lecture is kind of a mix. So the first part of it is going to be a bunch of phase diagrams and then a bunch of geochemistry, and I think both of those are quite hard. So when we get to the third part, we're just going to look at lots of pictures of Hawaii and relax a bit and talk about mantle plumes. So there is still some science in there, but hopefully it'll be a bit more chill. If you find the phase diagrams hard, that's completely fine. Like I was saying to Freya and some of the guys who were here earlier, I really only figured them out recently. I feel like they're not super intuitive, but hopefully if we kind of lead you through them slowly, then by the end of it, I'm hoping it'll twig like what the point in them is and why you would use them. Yeah, so there we go, we'll start. So before we go straight into phase diagrams, I'm going to quickly talk about the idea of different magmatic suites and different ways that we can describe differentiation. So at the end of last week, we kind of finished on this idea that you can get a range of different crystallization products. So these would be like different cumulate rocks, all crystallizing from the same magma. So we talked about that in the terms of a mid-ocean ridge, where you have these different layers. You have the ultramafic cumulates, then you have the gabbros, and then you have these dolerite dikes, and these are all broadly cumulates. And then you get some sort of leftover melt, maybe with a few phenocrysts in it, and that's your mid-ocean ridge basalt that's erupted at the end. So we basically see all these different things that have come from these different magmas, but we never see the magma themselves. By the time we get to a mid-ocean ridge basalt, when it's erupted, it's already quite evolved. Yes, Emma?
Can you clarify exactly what cumulates is?
Oh, yeah, absolutely. So a cumulate is a rock that is, it's mainly made up of crystals that have crystallized from a melt, and kind of they've settled in some way to make basically like a big pile of crystals. So this would be like, it would be like if you're freezing water, you get a layer of ice near the top, maybe. It'd be the opposite. You get this layer of crystals at the bottom of a magma chamber.
So it's just an accumulation.
An accumulation, yeah, exactly. Okay. All right. So I think this kind of leads nicely into the concept of different magmatic suites. Some people use series for this. Sometimes magmatic series means something else. So we'll just stick to calling them suites. So all these different rocks we talked about, the ultramafic cumulates, the gabbros, the dolerite dikes, and the morb, they have completely different compositions. They have different textures. When you look at them in hand sample, they don't look similar. But they all came from some sort of single parental melt, some sort of precursor magma, or a series of very closely related magmas. So they're mainly linked by differentiation. In the case of mid-ocean ridges, this is mainly fractional crystallization. So the crystals are crystallizing and they're being removed from the magma. You're leaving these cumulates, and then the melt that's left behind has a different composition. And that composition continuously changes as you remove crystals from it. So when we talk about these, all these different rocks, but they're linked, we can describe that as a magmatic suite. So in this case, this could be a mid-ocean ridge suite, or we'll get a bit more into this next week, but they're a type of basalt. It's a tholeiitic basalt, and these would all be cumulates from some sort of tholeiitic magma suite. Okay. So there's a bunch of different ways that we can describe differentiation and this evolution of magma. And I think you'll probably be kind of familiar with the first two. So the first one is one that we've used a lot in the practical exercises, is describing them in terms of mineralogical changes. And some of you might have heard me say last week that, okay, it's got olivine and plagioclase, therefore it's a basalt. Okay, so I think you would have seen Bowen's reaction series last year. Does this look vaguely familiar? So the idea here, it's named after one of the first kind of geochemists, and he had this observation that in general, as magmas cool and crystallize, you get this series of minerals that more or less indicates that the magma is getting more felsic, it's getting colder, it's crystallized more. So at the top, yes?
Are suites or series always cumulates, or are they just always a result from a parental magma?
I guess what I'm saying here is it would be all the melts and cumulates. So it includes the mid-ocean ridge basalt, and I don't know if we'll get into it this week, but we might see it in some of the subduction zone stuff. In some cases, it can be a series of magmas, right? You might see like andesites and rhyolites that come from the same suite, but they've got different compositions. Or you might see like basalts and picrites that come from the same suite. And we can talk more about that later. Yeah. Okay, so the idea of Bowen's reaction series is on the left here, you have ferromagnesian minerals, and this was described as a discontinuous series. So when you go down in temperature, there are these systematic shifts. So usually the first thing to crystallize is olivine, and then pyroxene, and then amphibole. You start to see that in andesites, for example, and then biotite, which you see in some intermediate rocks like andesites and dacites, and you also sometimes see it in rhyolites. On the right-hand side, you have this feldspar series that is described as a continuous series, and it basically starts with calcium-rich plagioclase, anorthite, and that evolves as the melt differentiates, as it becomes more evolved. Then the plagioclase becomes more sodium-rich, so it becomes more like albite or oligoclase here. This is one of those subdivisions of plagioclase that I'm not expecting you to remember. And then the last phases to crystallize are things like potassium feldspar, muscovite, quartz, and these are things that you see often in granites. This is basically the same idea as that kind of mineral modes diagram that I showed you in the previous lecture. Again, these are like broad guidelines. Not every rock suite is going to behave in the exact same way, but yeah. So we can broadly, using the minerals, describe rocks as ultramafic, mafic, intermediate, or felsic. So this is sort of like a qualitative description. We're not putting numbers on it. We're just saying this is more or less mafic, it's a basalt. This is more or less felsic, it's a rhyolite. The next way we can do it is using phase diagrams, and I have heard that you saw them a bit last year, but I'm basically going to start from scratch, so because I think these are super confusing, hard to get your head around. And I've described them here as semi-quantitative because we can start to put numbers to it, but really what we're doing in a phase diagram is we're representing a complex rock composition that's got all these different elements in it. You know, there's going to be usually a bunch of silicon, stuff like magnesium, calcium, aluminium, sodium, titanium, and basically people are simplifying this into what they think are the key elements, and they're usually representing it with some sort of minerals at the end members. So you might have seen stuff like the forsterite, anorthite, diopside, ternary phase diagram. We'll do a lot of this later this lecture. And so what this allows experimental petrologists to do is they basically use these simplified compositions, they melt them, they see what crystallizes at different temperatures, and they build up this kind of field, this idea of what is crystallizing where. And this allows you to make predictions if you have a rock with a similar composition about what order things are going to crystallize in. The reason I describe it as semi-quantitative is often we're missing out all these extra elements, and that means that these phase diagrams don't always perfectly match reality, but they're a good guideline, they're a good way of like trying to understand some of the concepts that we'll talk about more broadly in basalt crystallization. So this example is showing the granite eutectic. So this is like basically the lowest temperature granite before everything freezes. It's that dot in the middle that's at 660 degrees. And you can see often we look at these phase diagrams in 2D on the right, but this 2D is sort of like a contour map. It's like projected onto 2D. And the real phase diagram is this kind of 3D structure. Above that surface, the 3D surface, everything's molten. And below it, different minerals are crystallizing. And again, we'll talk about this much more later. But I just want you to keep in mind this kind of, we're squashing everything down. We're projecting these 3D fields into 2D just to make them more convenient to work with. The last one is we can use geochemistry and geochemical models. We're not going to do any geochemical, like any kind of hardcore geochemical modeling in this course, but we are going to talk about geochemistry and hopefully get used to kind of reading these geochemical diagrams and understanding what they mean. And I said last week we wouldn't talk about komatiite, but I couldn't resist. This is a couple of plots, titanium against magnesium on the left and aluminium against magnesium on the right. And basically there's a bunch of komatiite data, those are the blue diamonds, and from that These are some geochemical models that I ran showing how you could crystallize this to make a basalt. And the key thing to notice here really is that the way that these trends in the geochemical plots present, it reflects the minerals that are crystallizing. So early on, if we start on the orange cross on the right, we're just crystallizing olivine. So we're removing something that's very high in magnesium and very low in titanium and aluminium. So we push the melt composition away from olivine. So actually the melt composition is being pushed to the left from that orange cross in both diagrams. Later, we start crystallizing clinopyroxene in this case, and you can see that because there's an angle, the trend changes. And so we actually start pushing the aluminium up faster because neither clinopyroxene nor olivine have aluminium in them. And then eventually we crystallize plagioclase, which is really obvious on the right-hand plot. That's when the aluminium starts to plummet. And we can see that these basalt compositions broadly correspond to something that's crystallized, a bunch of olivine, clinopyroxene, and then eventually plagioclase. But yeah, we'll talk about this more later. So yeah, the main thing to notice here is when we're removing a mineral, we push the composition of the melt away from that mineral. Okay. So just to sum that up, magmatic suites, these are a series of igneous rocks, can be melts or cumulates, and they are from some sort of maybe one batch of magma or some similar magmas so that we can describe them as if it was one blob of magma crystallizing. These different rocks are linked by differentiation processes. The most simple one that we've covered a lot in the mid-ocean ridge system is fractional crystallization. There is, of course, crystal accumulation to make cumulates. And then sometimes assimilation, that's something we'll look a bit more at in terms of subduction zones. We can also describe these differentiation processes either by looking at the mineralogy, by using phase diagrams, or by using geochemistry. So most of this lecture is going to be covering phase diagrams, geochemistry. So, any questions about that? Okay. Yes?
How can you crystallize a magma to which, like the slide before, I didn't understand how you can do that and how you can remove a mineral from a...
So what's happening is if you imagine you have a magma chamber and some sort of magma comes in, fills it up from below. So you've got a blob of magma sat in the crust. It goes back to that thing we talked about yesterday where they don't all, rocks don't all melt at once, they don't all crystallize at once. So you start to crystallize it, right? As it cools, it starts to form crystals. And as you form those crystals, they're typically going to drop towards the bottom of the magma chamber and make cumulates. The crystals have a different composition to the magma. So we end up changing the composition of the magma by removing the crystals. Does that...
But we don't do it.
No, we don't personally.
Yeah.
This is a geochemical model, so this is just based on thermodynamic data. But what some experimental petrologists do is they're literally doing these experiments, right? Like take a rock composition, heat it up, melt it, see what crystallizes. And there's all sorts of different experiments. You could even do ones where you, let's say you have it molten 5%, 10%, 15%, and you can measure how the composition of the melt changes. So, yeah. But what we, again, coming back to that idea from the end of the last lecture, what we see in nature is we see these suites where we know that they're all linked and we can see that they're derived from some melt, but usually we have to kind of guess, we have to estimate the original melt composition, and then we can run some sort of models to try and understand how they crystallized. Yeah. Yes?
So if I put a piece of granite into a bonfire, then it would probably start to disintegrate and some of it would start to melt?
If you have a very hot bonfire, it'll start to,
Yeah.
So what's weird is the way these things melt and crystallize isn't necessarily the same way, but let's say you had a granite and you heat it up to 660 degrees C, you'd start to melt and you'd make something with a composition close to this ternary point. And we'll talk about eutectics in a bit. So,
okay.
Yeah. Yes. Okay. Phase diagrams. So I've included this textbook link in the week 49 module, and I think it does a really amazing job of explaining phase diagrams. As I said here, it discusses ice and chicken soup, and lots of, it's kind of boiling down these complicated geology concepts into things that are pretty familiar to us. So I'd really recommend checking it out after the lecture. Okay. So in terms of the types of phase diagrams, you've already heard me mention ternary phase diagrams. We also have binary phase diagrams. This just tells you how many axes we're using. So binary phase diagram has 2 axes. And you'll see lots of different types of these. An example on the left is a pressure-temperature phase diagram. So what it's showing is at a fixed composition, and in this case the fixed composition is just forsterite, it's just the magnesium end member of olivine. It's just showing at what pressures and temperatures it's liquid, it's fully melted, and at what pressures and temperatures it's solid, so it's an olivine crystal. That's it. On the right is one that you probably saw last year, which is a temperature composition diagram. And in this diagram, the pressure is fixed. So if we change the pressure, the diagram wouldn't look exactly the same. And the example here is a plagioclase binary. And so on the y-axis, the vertical axis there, we have temperature. We can see that above, say, 1500 degrees, every composition is melted. But depending on what composition we have, it will start to crystallize plagioclase at different temperatures. Underneath about 1100, everything is completely solid. And you can see this kind of loop, and this is to do with the fact that, again, we're not dealing with a single composition. So at high temperatures, you'll start to crystallize the calcium-rich plagioclase, while the sodium-rich plagioclase is still kind of, that composition is more in the melt. So yeah, hopefully you saw that last year. The next one is ternary phase diagrams, and these have 3 axes, so we put them in a triangular plot. These are almost always 3 different compositional variables. It would be really weird to see something that was like composition, temperature. I don't even know how you plot that. So basically, we have these 3 components, and the components make the corners. You can see here diopside, forsterite, anorthite, which is basically plagioclase, olivine, clinopyroxene. And the temperature in this one is shown using contours. You can see, so this contour here is a 1500 degree C contour, and this is a contour for where you just have olivine plus melt. So below this, it's going to be crystallizing. Above this, it's going to be completely molten. Not all of them show these contours, and sometimes you'll just see these down temperature arrows. And these kind of imply the temperature, but we'll talk a bit more about those in a bit. These are called cotectics, and then the eutectic is the coldest melt, the coldest temperature where you can have any melt. So yeah, this ternary diagram is particularly relevant to basalt crystallization, so I'll probably talk about that quite a bit. I wanted to kind of show you what the relationship between a ternary and a binary plot is. So if you have a temperature versus composition binary plot, what you're actually seeing is it's kind of like a cross-section through one of the sides of a ternary diagram. So I hope this will help you visualize it. Here we've got a forsterite quartz compositional axis, and then we've got temperature on the y-axis. Now, if we look at this ternary plot, on the bottom axis of the triangle also is forsterite and quartz. This one only goes up to 50% quartz, so it's basically stopping here. But if we follow this, we can see this is the forsterite saturation surface. This is where forsterite starts to crystallize. And if we look at it, we then have this little boundary here where you have enstatite starting to crystallize. And to the right, we have cristobalite, which is just the high temperature form of quartz. Now, if we look at this diagram and follow along that axis, we can see the same thing. We've got forsterite crystallizing, then we've got this little zone where enstatite is crystallizing, and then we've got cristobalite. So basically, this is a cross-section through this half of this axis. Does that make sense? Because I think this is a really kind of important point. Okay. So when we look at these contours, we can actually match them up. 1800 here, that's matching up with this point here. 1700 a bit further in, that's matching up with this point here. Okay? Yeah. There's a couple of rules that we're going to learn about for dealing with phase diagrams. The first one is the Gibbs phase rule. And this one will seem a little like wonky at first, but hopefully it'll make some sense. It's a really simple equation. F equals C minus P plus 1. F is degrees of freedom, and this is kind of like a bit of a nebulous concept at first, but like what it's saying is essentially what ranges of temperature, pressure, composition can this thing exist at. C is the number of chemical components, so these are these N members. So in this case we have forsterite and quartz, so it's a binary, there's 2 chemical components. P is the number of phases, so these are either minerals or liquids or even gases, you know, that kind of thing. So if we just have a look at this quickly, if we look at the liquid field, the number of components we've said is 2. We've said the number of phases here, that's just 1, right? Because you've only got a liquid, one phase, plus 1. So we can do this. F equals C, 2 minus 1 plus 1 is 2. And what that means is that the liquid field can exist over a range of compositions and a range of temperatures. Right? If we look at this field here, forsterite plus liquid, number of components is still 2. The number of phases is 2 because we've got forsterite, which is basically olivine, and we've got a melt as well in this field. So 2 minus 2 plus 1 is only 1 degree of freedom. And that means that if we know what the temperature is, there's only one composition where forsterite and liquid can exist together. If we know what the composition is, there's only one temperature where forsterite and liquid can exist together. And finally, if we deal with the eutectic point, here we have enstatite, which is basically orthoperoxene. We have cristobalite, that's our high temperature form of quartz. And we've got a melt at the eutectic. 2 components still. Minus 3 phases is minus 1. Plus 1 is 0. So that means there are no degrees of freedom. If we know that the composition and the temperature are fixed, we can't, that it only exists at one temperature and one composition. Okay? So that's the difference between a field, which in this case has 1 phase, a line, which in this case has 2 phases, and our eutectic point that has 3 phases. So it only exists at one temperature. Yes?
I need to understand this.
Yeah.
The field called forsterite and liquid.
Yeah.
Are you saying that you cannot be inside that field? You need to be on the graph that
yeah.
is between liquid and forsterite.
So the thing that happens here is if and I'll talk about this in the next section. But if we have this melt that with composition A and you cool it, it hits this line and it starts to crystallize. And so we're both making pure forsterite, because we can't make any other olivine because we've only got magnesium and quartz basically. You start to make pure forsterite, and as you remove that, the liquid composition changes. And as it keeps cooling and crystallizing, it basically sticks to that line. So it can't sit in this field. Same thing for melting. If I bring the temperature up, as soon as I'm in forsterite plus liquid, I'll start making melt over here. And the composition of the leftover residue is going to change, and we're going to start moving up this line. And then eventually, once everything's molten, we can leave that surface. So yeah, it seems weird because it looks like, oh, why wouldn't it just sit in there? But it can't. So okay. The other one is the lever rule, and this is just a way of figuring out what proportion of each phase is either crystallizing, or we can calculate how much melt is left from something crystallizing. So I think the equation for it looks a little complicated, but we can just look at this, right? So this is in one of these binary phase diagrams, and you saw it in the plagioclase binary. We had this liquidus, everything above the liquidus is molten. We had this solidus, everything under the solidus is solid. But we can have things in the middle, right? So at that point we have a liquid and a solid that are in equilibrium. So here, if we have this composition at this temperature, we'll have a certain amount of liquid with composition C. We'll have a certain amount of solid with composition D. Essentially, if we were sat all the way over here, we'd have 100% solid with composition D. If we're sat all the way over here, we'd have 100% liquid with composition C. And the lever rule is just for calculating what the proportions are in between. And you can think of it as this kind of balance, like it's a lever. This is where the name comes from. So the closer we are to D, the more solid we have. The closer we are to C, the more liquid we have. And you can think of it as this balance. So the more weight you put on one side, the closer the pivot point needs to be to that side, right? So this looks messy, but we can basically guess it. So I would say from C to X is about 3/5 of the way from C to D. Does that look about right? Just totally pulling numbers out here. So in that case, we would actually have 60% of D and 40% of C. So basically, we're just flipping it around. So the closer you are to one end, the more of it you have. The closer you are to the other end, the more of that you have. Does anyone have any questions about that? I'm seeing some confused faces. Okay. Maybe I think we'll practice this in the practical exercise. Maybe So don't be intimidated by this. We can just do it as kind of rules of thumb here. Yeah. So I've got an example here where we're using the lever rule applied to a basalt phase diagram. This one is a binary diagram between diopside and anorthite. So again, this is like clinoproxene, plagioclase. And this is relevant to basalts because we have loads of plagioclase and clinoproxene crystallizing. So if we start with our melt with composition A, and this is it's 80% of the way along. So it's 80% anorthite and 20% diopside. You can see that lever rule here, we're closer to anorthite, so there's way more anorthite. When this starts to crystallize, if it cools down, it will start to crystallize here. The melt composition will evolve along this line, and we're just crystallizing anorthite, right? Because we're on this anorthite plus melt field. Once we get down to this temperature here, which is, if we draw a line down, we're at 72% anorthite left in the liquid. And the solid is obviously 100% anorthite, because that's what we can crystallize. We can do the lever rule. So this is our position X. So 80 minus 72 divided by 100 minus 72, and that's 28.6%. So we have 28.6% anorthite, because we're further away from this one, right? And we have 71% liquid left. Does that make sense? So remember, the one that we're closer to is the one that we have more of. So at this point, we're much closer to the liquid than we are to anorthite. If we keep crystallizing this, do I have this as a slide? Yeah. Okay. So if we keep crystallizing it, and we get all the way down to the eutectic point, here, the melt has a composition with 42% anorthite. The solid, again, yes?
Didn't you just say it could be in that field of the phase?
So that's the overall composition is in this field, but the composition of the crystals is over here, and the composition of the liquid is over here. This is just the average.
Okay,
yeah. Yeah. Okay, so once we hit this eutectic, diopside is going to start crystallizing, because we're now at this diopside plus anorthite, but we've still got the melt just touching here, right? So we're going to take this just before the diopside begins to crystallize. So at this point, the liquid is 42% anorthite, the solid is 100%. We do our lever rule again, 100 times 80 minus 42 divided by 100 minus 42, and that's 65.5. Because our overall composition is closer to anorthite, so we actually have more anorthite. It's further from the liquid, so we have less liquid. If we keep crystallizing it, and we crystallize everything, so we get past this eutectic point, this is the average composition still, then we just have this mixture where it's 80% anorthite, 20% diopside. So this is just the solid version of what we started with. Everything's crystallized. Okay, does that sound... Yeah, good? Oh yeah, I had actually a slide for this. Yeah, so when we actually start to crystallize diopside, the temperature actually stays constant. The reason for this is that the crystallization is exothermic. We're at a eutectic, so we can't go down any more temperature until we've crystallized everything. So we basically sit at this eutectic point. If we do our Gibbs phase rule, we have two components, diopside, anorthite. We have three phases, because we've got diopside, anorthite, and liquid. We have no degrees of freedom, so it just sits there at that same temperature. And yes, that's it. And then once crystallization ends, we've got 80% anorthite, 20% dioxide. Okay. Moving on to Ternary diagrams, and this is just a bit about how you plot on them. We have this same idea with the lever rule, but instead of doing the distance from the edge of the diagram, which is very easy to do on a binary diagram, you have to do it by drawing. So if this is your actual composition in the black circle, then you basically draw a line between the end member and the far side, and it's the lengths of these two lines that go into your lever rule. So you can see it up here. When it comes to plotting on a ternary diagram, we often have these kind of guidelines, and you can see when you get to one of the corners, you have 100% of that component. So this one's 100% quartz, this one's 100% plagioclase, this one's 100% feldspar. So if we wanted something with 40% feldspar and 40% plagioclase and 20% quartz, then we follow this line, 40% feldspar, that intersects with 40% plagioclase, and we have 20% quartz, so it'd be a dot right here. Okay. All right, so just to sum that up, phase diagrams, they're a way of showing what minerals, or sometimes liquids like melts, so these are phases, will exist at a given temperature, pressure, composition. And usually we're using a set of end-member components to describe this. So ideally you want components that all of your actual compositions sit as some mixture of these different components. And the important rules to remember when it comes to this are the Gibbs phase rule, which is degrees of freedom is the number of components minus the number of phases plus 1. And the lever rule, which is this balancing act, right? The closer we are to one end, the more of that component we have in the mixture. Does anyone have any questions about that section? Yes?
So, for an exam question, what would you ask if you gave this kind of...
I don't know. We'll get there when I figure it out. Okay. But yeah, I think I would try and remember this, and if you can, probably a good idea to try and remember both of these rules, but I mean, you know, yeah, I'm not sure in terms of exams.
Okay.
Yeah.
The lever rule.
Yeah.
Could
Yes.
you say that again, maybe?
Oh yeah, yeah. We'll just go back. I need this diagram for it because it doesn't mean anything without it. So all we're doing, this is the percentage of D in this case. So the percentage of this side of things is just 100 times the average composition minus the other composition divided by the one that we're interested in minus the other composition. So, yes?
You said 60% D.
Yeah, this was just as a rough guess. I was saying, yeah, so if this...
But it's 40% on that side.
Yeah, so whatever we're closer to, we have more of. It does feel counterintuitive, but if you imagine if this was right, if X was sat right here, we've got 100% D, right?
Yeah.
So the closer we are to D, the more we have. And that's, so what we're saying here is that the amount of D that we have is this kind of weight on the balance. Mm-hmm. So the more weight we have on that side, the shorter this distance has to be to make it balanced. Mm-hmm. Yeah. Okay. Anyone else? Okay. All right. So I'm going to try and talk through some of these and how they apply to basalt crystallization. We'd already talked about briefly how we can use this olivine phase diagram, and this helps us understand why mantle melts are less magnesium rich than olivine. The reason for this is if we have mantle olivine, which is sat at Forsterite 89, we can see that whatever liquid forms in equilibrium with that has to be at the same temperature, right? Because it's at equilibrium, and that exists over here. So for mantle olivine with Forsterite 89, then our liquid maybe has Forsterite 60 or something, reading off this diagram, right? Again, for real melts, it's not going to be exactly like this because we don't just have Forsterite and Fairlight, we have all sorts of other things in there. But this still applies. Whenever you melt the mantle, the olivine, the melt is going to have a lower Mg number, it's going to have less magnesium relative to iron than the olivine in the mantle. We can use the same reasoning. So in this case, we were talking about moving the mantle up temperature, or in practice, we're reducing the pressure, which has the similar effect. What if we have a basalt? If we have a basalt somewhere up here and we start cooling it, once it hits the liquidus, it will begin to crystallize, and the crystals that form from it will always be more magnesium rich, or have a higher magnesium over iron ratio, Mg number, than the liquid itself. Okay. We can use a similar thing to explain why plagioclase becomes more and more sodium rich the more we crystallize. Yes?
I have a question with the, if we have a melt, would it always start to crystallize at 1,800 temperature?
No, it depends on the melt composition. Yeah, it totally depends on the melt composition. So if we had a melt that was pure Fairlight, it only starts to crystallize at 1200.
Yeah. Yes.
If we have a melt that's pure Forsterite, it only starts to crystallize at 1890, and you can have everything in between. But it's always going to start to crystallize on this surface. These temperatures are all quite high, right, compared to what you might know of basalts. And the reason for that is because this is pure olivine. Real basalts aren't pure olivine. But we're just using this to explain to understand the concept of these changes in Mg number. Yeah.
So just to make sure, once you hit the liquidus with that blue star right there, the first crystals we get are then
the green ones.
Yeah, the Forsterites of that amount of olivine with that amount of Forsterite.
So if we took mantle that has relatively shallow, so that this isn't changing too much, we melted it, we made a basalt, and then we crystallize it a little bit later, you probably end up with olivine which has similar composition to the mantle that it came from. It does change a little bit because this all changes with pressure, but broadly, yeah, if we're getting mantle melting and we start crystallizing olivine without doing anything to that melt first, it should also have Mg number of about 89. So, yeah. So with plagioclase, we have a few more lever rule calculations here, but if we start with a melt composition here, this is above the liquidus, and we have albite on this end and anorthite on this end, so that's the calcium-rich plagioclase and sodium-rich plagioclase. If we start crystallizing, we come down here, the first crystal that we form it's got to be at the same temperature as the liquid, right, because everything's in equilibrium. We draw a line across, and we have something crystallizing with 71% anorthite. Because we're removing something that has more anorthite than the liquid composition, we're pushing the liquid down this kind of envelope here, and subsequent plagioclase is going to be less anorthite rich because we've already removed anorthite. It's in the crystals that are formed. So you can see here at the liquidus we got 100% liquid. Once we've crystallized down to 1350 degrees C, we have about 2/3 liquid, right? We're lever rule, so it's the opposite way around, and about 1/3 plagioclase crystals. By the time we get down to 1250, most of it's crystallized. We only have 17% of the liquid left because we're very close to this crystal composition. And then finally, when we get down here, the last plagioclase to crystallize is really sodium rich. So we've only got 7% anorthite left, but we've got no liquid left. So after that, we just have this mixture of plagioclase crystals with a different composition, but the average is the same as the original starting melt composition. So, yes.
I just need to make sure.
Yeah.
So that once you have crystallized all the anorthite,
Yeah.
then you end up with pure albite.
No, the last plagioclase to crystallize would be very, very albite rich,
Okay.
but then the average composition ends up the same as the start.
And it is shown here as arrows going down. But is it correct that the real thing that would happen is that the temperature will remain constant while the remaining crystals crystallize?
No, it wouldn't in this case because it's not a eutectic point. So if we do our Gibbs phase rule here, we've got two components, we've got two phases, right? We've got liquid and we've got plagioclase. And so 2 minus 2 plus 1 is 1. So it actually crystallizes at a range of temperatures. Yes.
So in the middle, when it says there's 34% melt and 66%, 66% melt. And
Yeah.
Is it so? Is it like the chemical composition, or is it the like melt and crystals it's describing?
So the crystal composition is over here, the melt composition is over here, and so the composition you would just read off.
Yeah, then you just pull down and read.
Yeah.
And the lever rule describes the mix between.
The amount of melt, the amount of crystals. Yeah.
I think I had a bit of trouble with your average.
Yeah.
How did you get to that conclusion? Let's say you did the one above that. Let's say you take the second line, the one at 1,350.
1,350. Yes. Yeah.
When you do your average there.
Yeah. So the
Then
plagioclase.
take it out to the solidus line.
No, so it's just the average composition is just staying the same throughout, right? But up here we've only got melt with that average composition. Down here we've only got plagioclase with that same average composition, and in between we have mixtures of plagioclase and melt. I should also stress it's a little confusing because like most of the stuff we're going to talk about is fractional crystallization, but in these phase diagrams, because these are experiments, right, that people have run, everything is in equilibrium. So I slightly misspoke before. This 7% anorthite. That's the composition of the last melt before everything crystallizes. But what happens with equilibrium crystallization is we're not crystallizing 71% anorthite and removing it. We're crystallizing it and leaving it in contact with the melt. And actually, as the melt cools, the composition of these plagioclases is going to equilibrate. It's going to shift around to fit what the melt's doing. So I hope this makes some sense. Yeah.
Can you do the Gibbs calculation for this one again?
Yep. So up here, if we've only got melt, the number of components is 2, binary. Number of phases is 1, and so 2 minus 1 plus. Sorry, I've done this right. Two minus 1 plus 1 is 2. Yeah. So the melt can exist at a range. If you give me a composition, the melt can exist at a range of temperatures still. Right. So at this temperature, we can have melt at almost every composition. So it's a field because there's 2 degrees of freedom. If we're on this liquidus, we're crystallizing. So we have melt. We also have plagioclase that's crystallizing from it. Components are 2, the number of phases is also 2, so the degrees of freedom is 1, and that means if I tell you a temperature, you can instantly tell what composition of the melt is. There's only 1 degree of freedom. It can exist at a range of temperatures, but it's not. You can't pick any composition in any temperature. If you have a temperature, you know what composition it is, and vice versa.
Okay.
Yes.
So what would it mean if they were like the number 2 instead of 1? Would that mean that it had?
If we have 2 degrees of freedom, it's a field. So melt can exist at a range of compositions and a range of temperatures.
Okay.
Yeah. Whereas this one, if you know the temperature, you know the composition. So it can vary. The temperature and the composition can vary, but they are related to each other. So they're not free of each other. So you have 1 degree of freedom.
What's the maximum degrees of freedom?
Depends how many components you have.
But you could have 10 degrees of freedom.
Yeah, sure. But you have to think in 10-dimensional graphs, which is getting really messy at that point. So yeah, if you have 10 different components and you only have 1 phase, then there are 10 degrees of freedom. So that would be saying it can exist over this range of compositional space, plus a range of temperatures maybe.
Okay.
Yeah. Yes?
But you can't talk about the level if you don't know the starting composition. If you're like looking at the liquidus as a one freedom, right? You have one freedom on the line, so let's say 1300.
Yeah.
You know exactly the composition when you reach the line. But you don't know.
You know the composition of the melt that's crystallizing.
Right.
You also know the composition of the solid.
Right, but you don't know the
So-
average melt, right?
No.
Because you don't know what the starting composition was. So you can't use that level,
No.
right?
That's a very good question. Yeah, I think so. There are a range of starting compositions that could end up with a liquid here
Yeah.
and a crystal here.
Okay.
But you kind of would need to know that, otherwise I think it's a bit not sure what the use is.
No.
Yeah. Yeah, but yes, you would need to know what the composition is overall. Okay, let's keep going. Let's go on.
You go. If you start with that composition as in the diagram.
Yep.
And you just keep cooling down.
Yep.
Is it correct that the final melt would be pure alkaline?
No, it's here.
It's here.
It's here, and the reason for that is because at this point we've crystallized everything. If we did fractional crystallization rather than batch, which is more realistic in nature, because we're always removing more anorthite, eventually we would run all the way down to here. But with fractional crystallization, the final melt and crystals are separate, right? You've removed those crystals, so you can actually change the bulk composition. But with equilibrium, we are stuck where the average composition between the melt and the crystals has to stay the same. And just at this point, once you get down here, you've got no melt left. So.
And so the remaining melt, no, there's no melt left at all?
There's no melt left with this composition. When we hit this point, we run out of melt. As long as if it's equilibrium,
Yeah,
then
so everything will be solid? at
Everything is solid.
60 degrees?
exactly, yeah,
Okay.
and it's got that composition.
Okay, great.
Yeah. Okay. All right. I've already kind of mentioned eutectic points, but let's do it a bit more formally. So at a eutectic point, we have 0 degrees of freedom. So there's only one temperature that this can exist at, and there's also only one composition. You can't move it at all, right? It's a point. So no freedom. Americans would hate it. But if we look at this, degrees of freedom, a number of components, minus the phases, plus 1. So for a binary, we have 2 components. We have, to get 0 degrees of freedom, we have 3 phases. So in a binary system, 3 phases is a eutectic point.
What are those 3 phases?
In this diagram, it is dioxide, anorthite, and melt. So basically CPX, plagioclase, melt. So what would happen here is if we crystallize melt A, we start off, we're in this, we hit this anorthite and melt field. So we start crystallizing anorthite, and we start moving the melt composition down as we cool, because we're putting anorthite into the solid. Eventually, it hits this point, the eutectic, marked E, and then it basically just sits there at that temperature and crystallizes dioxide and anorthite. Now in this case, the proportion that you're crystallizing at this eutectic point, where the eutectic point sits at 42% anorthite. So if we do our lever rule again, I'm just going to say this is about 60%, this is about 40%. So we're going to be crystallizing, well, we can be really exact, we're going to be crystallizing 58% dioxide, because we're closer to dioxide, and 42% anorthite, because we're further away from anorthite. So we just sit at that temperature, crystallizing plagioclase and anorthite and dioxide in those exact proportions, and it keeps crystallizing until everything's gone. So we enter this temperature with some melt left, but we can't leave this temperature until all the melt's crystallized. Now again, this is something about phase diagrams that doesn't necessarily translate super well to a lot of natural systems, because if we think about a real basalt, like we crystallize clinocroxene and plagioclase, and then some of you guys will have seen in the thin sections, you then start getting things like iron titanium oxides. These aren't represented in this diagram. So in reality, it's not just going to sit there and crystallize at that temperature, because the melt's going to keep evolving and it's going to crystallize different minerals. But for these kind of diagrams where we've got a simple system with only two components, that's how it behaves. Yes?
Why does it go all the way down to 1200? Like, what's the point of showing that?
Just to show a bit of the solid field.
Okay.
Yeah. So yeah, anything under here is just diopside and anorthite, and if your composition was over here, you'd have 80% diopside and 20% anorthite. If your composition was over here, you'd have 80% anorthite and 20% diopside. But yeah, so there's one reason for this, and I don't think I'm covering any of them, but some phase diagrams you actually have changes below the solidus. So I think Chris mentioned you've done Perthite exsolution. This is where you get those. Yeah, okay, Bastian's nodding. At least one of you remembers it. So Perthite exsolution is where you get those exsolutions of K-feldspar and plagioclase. And that's because there are changes below the solidus. So you get, potentially if we kept cooling this, maybe you get different minerals, right? But in this case, we've cut it off at 1200 because we're only interested in the crystallization. Yes?
So if you have a starting melt that will cool down exactly on the Eutectic point, everything will crystallize at the same time.
Exactly. Yeah, if we started with a melt that had 42% anorthite, and we just cool down, nothing is crystallizing through this whole bit, we hit the Eutectic and we'd actually start crystallizing plagioclase and, anorthite and diopside at the same time. So this would be, kind of a unique case.
So if it drops one temperature, everything will crystallize?
Yeah, it will just,
immediately.
No crystals until, it's not immediate because it's an exothermic process, this crystallization. So we need to keep cooling it. So we're losing heat, but the temperature's not going down because as we make crystals, that releases heat. So the crystal, the heat from crystallization is being removed, but the temperature's staying the same. Yeah. Okay, ternary phase diagrams. So it's a little different because we have three components, but it's the same idea. A ternary eutectic, to get 0 degrees of freedom, right? We said eutectics have 0 degrees of freedom. We need to have 4 phases. We can do that from the Gibbs phase rule. Degrees of freedom is the number of components. We got 3. We need to subtract 4 plus 1 to make 0. So in most of these, those 4 phases are going to be 3 minerals plus a melt. So I just want you to keep this 3D visualization in mind on the left. And you can see the eutectic point there is the lowest temperature. So these surfaces in 3D are the temperatures at which you'll have, a mineral, one of the mineral end members with a melt existing. So at the eutectic, we're at the lowest temperature possible, so we're in the deepest valley. There's another thing in ternary diagrams which does not exist in the binary ones, and that is a cotectic. So in a ternary, that's going to be 2 minerals plus a melt. That's 3 phases. So our degrees of freedom, we have 3 components minus 3 phases plus 1 is 1. And so this is the same idea as, this is like the 3D version of those crystallization surfaces we were talking about. If we know the temperature, we know the composition. So along these cotectics, you have 2 minerals plus a melt. So this is just A, B, C labeled here, but if we start with the melt over here, it starts crystallizing A. It moves away from A until it hits the cotectic. Then it crystallizes A and C, because we're on the boundary of both of those fields. And it moves down this cotectic until it hits the eutectic, and then it crystallizes A, B, and C. And if we wanted to calculate what proportions these are in, we do that 3D lever rule I was talking about, where you draw lines from the components through the eutectic to the other side, and that will tell us the proportions. Okay. So the biggest thing to remember here is for a ternary system, eutectic, that's the lowest, well, for a ternary or binary, eutectic is the lowest temperature melt. In a binary, that's going to be 2 minerals in equilibrium with a melt. In a ternary, that's going to be 3 minerals in equilibrium with a melt. And in ternary systems, we also have cotectics that crystallize in 2 minerals at the same time. All right, so let's try and apply this to figure out what crystallization order we have in a basalt. So again, this is the anorthite diopside forsterite. It's basically plagioclase clinoproxene, and olivine. So useful for basalts because those are the minerals we see in basalts. Most melts coming out of the mantle are going to plot somewhere in this forsterite field, and that means that olivine is the first to crystallize. So if we start with composition X and we crystallize olivine, we're removing olivine from the melt, so we push the composition away from olivine. If we start with composition Y, we're removing olivine from the melt, we push the composition away from olivine. So the direction that we're pushing it actually changes because the melt compositions are different. The stuff we're removing is the same, but we're always moving away from this forsterite corner. Yeah.
When you cool down on the topographic map, whatever thing, does
Yep.
it always go diagonally onto the lines, or like?
I don't think so. I actually thought about this. I'm not sure because if you imagine a melt here, it's going to move away from A. So it's not like water rolling down a slope.
Okay.
It's moving away from the corner. So I think it seems like a lot of them it's almost perpendicular, but I don't know whether it has to be or not. Yes.
It would be circles if they were always perpendicular. I think they would be.
Yeah, it should always meet this edge at right angles.
Right angle,
Yeah, yeah. Yeah, there was another question.
It was, yeah.
Yeah.
If you had a starting melt in the middle of forsterite, for example, which way would...
It's always moving away from this
One way
corner.
you can see which way it
So-
would...
Always moves away from the corner. So if this was the starting melt composition, we can just draw a line from the corner through it, and we can see which direction it's going. So X, it's going that way. Y, it's going that way,
Okay.
and somewhere in the middle, it's going like that.
Yeah.
So it's always moving away from that corner because that's the only thing that's crystallizing. All right. So what you can see here is that the crystallization order in the basalt is actually going to depend on the starting composition. If we start at X, we're pushing away from olivine. We're going to hit this forsterite diopside cotectic first. So we're actually going to crystallize olivine, then CPX. If we start at Y, move away from forsterite, we're going to hit the forsterite anorthite cotectic first. So this is crystallizing olivine and then plagioclase. And then for both situations, we end up moving along the cotectics and we end up sat at the eutectic, where we're crystallizing some mix of olivine, plagioclase, and clinoproxene. You can see here that the eutectic is really far away from olivine, so we're actually not crystallizing a lot of olivine. We're mainly crystallizing, I think this ends up being about 50-50 plagioclase CPX, and then a little scrap of olivine. So, wow, would you look at that? Someone made a diagram for this.
I just need so what you're saying is that the olivine that is initially what would you say, crystallized from the melts would dissolve again.
It's not that it dissolves. So because these are equilibrium, it's like the composition of the minerals is adjusting as the melt composition changes. But in this case, so we don't have any solid solution because we've just got forsterite. So actually the composition of the olivine is always pure forsterite. So it only comes down to some of the binary diagrams we looked at had solid solutions. So you had ferrite and forsterite, and then the composition of the olivine will adjust. But here we can only have pure diopside, pure anorthite, pure forsterite. So it's just the proportions of the minerals that are adjusting during crystallization. Yes?
Every starting melt composition will always in the eutectic point.
Yeah, so we're talking only about crystallization here. When you're melting, yeah, kind of. It's a little more complicated because all of these are constant pressure, right? And all of the melting we've talked about here is decompression melting. So actually with decompression melting, what's happening is we're not raising the temperature. It's like we're moving the diagram downwards because the solidus is getting lower with pressure. So I wouldn't worry about it too much at this stage. We'll talk about it a little bit in terms of making tholeiitic and alkali basalts later. But yeah, the melt would be close to the eutectic. It's probably more relevant for crustal melting when we make a granite. If you take a rock and you metamorphose at really high temperature and it's a gneiss and then it becomes a migmatite, right? Those first melts formed are very close to the eutectic, the granite eutectic, so 660-ish degrees. Yeah, but obviously it's the composition of the melt you're going to get, and even the position of the eutectic is going to vary with the overall rock composition. Yeah. Okay, so for crystallization from Y, like I said before, we go olivine, olivine plus anorthite, and then olivine, anorthite, olivine plus plagioclase, olivine, plagioclase, clinopyroxene. From position X, we start crystallizing at a higher temperature because we're closer to here. If you remember the contours, we're close to 1700 degrees C. So we crystallize a lot of olivine, then we crystallize clinopyroxene, and then we end up crystallizing olivine, clinopyroxene, and plagioclase. So hopefully some of you would have done the crystallization orders in some of the basalts, and this is what we generally saw. I think a lot of those basalts went olivine, then plagioclase, and then clinopyroxene, but at least one of them went olivine, then clinopyroxene, and plagioclase. So this is kind of how we can relate these phase diagrams to real processes that are going on. We could say that, you know, the basalt that went olivine then clinopyroxene was probably closer to this end of the diagram in terms of composition than the one that went olivine and then plagioclase. And then more broadly, this kind of crystallization sequence that I was talking about, olivine, then olivine plus plagioclase, or olivine plus clinopyroxene, and then finally having all three crystallizing. This is really similar to our section through the oceanic crust, because at the bottom we have our ultramafic cumulates. These are dunites or troctolites, olivine plus plagioclase, or the whirlites, I think, which is olivine plus clinopyroxene. And then we get into a gabbro, which is basically all three, right? So this is us going from a melt that's only saturated in olivine. We're in that forsterite field, we're getting dunites. We then get to one of the cotectics, either plagioclase plus olivine or clinopyroxene plus olivine. And by the time we're crystallizing these gabbros, we're close to this basalt eutectic, so we're crystallizing all three. And then the melt that's left behind, because we didn't freeze it all, is going to make our morbs. So this would be like, we got pretty close to this basalt eutectic, but we didn't crystallize everything. We have some leftover melt. That gets erupted. That's a morb. Okay? So hopefully we can see like some reason for using these. Yep. All right, so nice one for staying with me through that. So yeah, phase diagrams, these give us a way of explaining certain mineralogical composition changes we see. So olivine goes from magnesium-rich to iron-rich as we cool and crystallize. We also have plagioclase going from calcium-rich to sodium-rich as we cool and crystallize. And they can also help us explain these crystallization orders that we see in basalt. And the reason that we start off just crystallizing one mineral and then we end up crystallizing these kind of three big ones. Yeah, Bastian?
Okay, I'm just a bit confused about the last point. First you crystallize dunite,
Yep.
which is pure olivine,
Yep.
more or less. But where are you crystallizing only more or less two minerals?
So these troctolites or whirlites, they're also in the ultramafic cumulates.
Yeah.
So troctolites, olivine and plagioclase. Whirlite is olivine plus clinopyroxene. So they're also in the ultramafic cumulates.
Okay.
But yeah.
Okay, was that the sort of left behind stuff?
So we do olivine first,
Yeah.
and then we start to crystallize the second phase. That's when we're on the cotectic. And then we start to crystallize all three, and that's the gabbro. That's at the basalt eutectic. Yeah. Okay. Great. Does anyone have any more questions on that section? Okay. We just got one little last thing to do, and that is peritectic reactions, which I think you also will have seen before, but I'll just go through it again. And then just a caveat with thinking about these. So we've already talked about eutectics. That's the lowest temperature melt. We got no degrees of freedom, just at one temperature. We've talked about cotectics, which is where we have two or more minerals crystallizing at the same time. In a ternary plot, it's always going to be two minerals on a cotectic. And the last one that you need to learn is peritectic reactions. And this is where, instead of having a melt that's crystallizing two crystals, we're taking a melt with one composition and we're actually reacting it with an existing mineral, and it creates another mineral and a different composition of melt. So I've written this here. Instead of having liquid, our melt that we've always had, we have forsterite plus liquid 1. So olivine plus 1 liquid equals enstatite plus liquid 2. And so what we can do is we can start with composition A here. So if we're cooling this, we hit the forsterite plus liquid surface, and this is in the forsterite quartz binary that I showed you before. When we hit this surface, we start crystallizing forsterite, and the melt composition evolves all the way down here. We're still on the edge of this forsterite plus liquid field. Melt comes down here, and then there is a change, and the next field is actually enstatite plus liquid. So it's not enstatite and forsterite plus liquid, it's only enstatite plus liquid. So when we hit this point, we have two minerals, we have forsterite and enstatite, and we have a liquid. So we have three phases, we only have two components, so that means we have 0 degrees of freedom again. So this peritectic also only exists at one temperature. Yeah, so I think once we get to this point, we start reacting forsterite plus liquid goes to enstatite and another liquid, but we actually can't keep going down here because we end up with a mixture of forsterite and enstatite. So actually everything crystallizes at this peritectic point. But the thing that's different from before is we actually consumed some of the forsterite that we crystallized to make enstatite. So we end up with this same composition A here, but it's a mixture of enstatite and forsterite, and we partly dissolved the early crystallizing forsterite to make that enstatite. If we came down this liquid composition B here, then we actually we have more silica, we have more quartz. We actually just crystallize enstatite, and then we eventually end up at this eutectic, where we crystallize quartz and enstatite, or cristobalite. This is the high temperature version of quartz, and so we'll just crystallize that like a normal eutectic. But if we're on this side and we're crystallizing olivine first, we get down to this peritectic, we partly remove some of the olivine, replace it with enstatite, and we end up with this mixture of forsterite plus enstatite at the end, underneath our original composition. Yes?
So all of the forsterite is consumed by the time we move?
No, I was wrong when I said that first, sorry about that. It's partly consumed.
But in the eutectic you only crystallize enstatite?
Yeah, so with this, if we're over here, we'll never get to the eutectic.
Okay, so
because once we're past this peritectic, the average composition goes through forsterite plus liquid, and it ends up at forsterite plus enstatite. So we do that by reacting the liquid with the forsterite to make enstatite.
So you never move from the peritectic point to the eutectic point?
Yeah, the peritectic, it just sits there. So the average composition stays the same. We're just reacting away forsterite, and then we end up with this mixture. We have less forsterite than before we hit the peritectic point, but it's not all gone.
But you would never you never start crystallizing quartz from a melt that started with the...
I don't think so, no. So this is something we'll talk about later, but this melt is, we'll talk sometimes about silica oversaturated melts. These are melts that are capable of crystallizing quartz, and these melts are not, they are not capable of it. Right, so sorry about that, I confused myself. Okay, so if we take this into a ternary diagram, so this is a ternary diagram that might be relevant to silica-rich basalts, and we can do the same thing as we were doing with the anorthite diopside forsterite diagram. So if we start with a composition at U, we're just going to crystallize forsterite, and then we're eventually going to hit this. This is actually a peritectic between forsterite and enstatite. And you remember we just saw that in the binary diagram. This corresponds to this side again, as mentioned before. So at this point, we are doing this reaction. Forsterite plus liquid 1 makes enstatite plus a liquid with a different composition. And we eventually move all the way down to this, this peritectic point here. And I think, again, I got this slightly wrong. So the plagioclase begins to crystallize. So we're crystallizing plagioclase and so anorthite and enstatite, and we're consuming olivine. We're consuming forsterite. So you can ignore this bit. We're not going to get rid of all the olivine. We're going to partially consume it. So this seems so basically this makes a norite. These are rocks that are orthoperoxene and plagioclase. And this probably seems a bit abstract, but you do see this. And if anyone looked at the SWE 21-4 samples, these actually had examples of this. This is from the BN dikes again, just because I had a good picture. But you end up with these big orthoperoxene crystals, and inside you've got these tiny little remnants of olivine. So this is olivine that is, it's rounded, it looks really unhappy. It's been partly consumed to make orthoperoxene. So it's actually, the rounded edges come from where it's been dissolving. So yeah, it doesn't happen, say, in like mid-ocean ridge basalts, but this is very common in basalts that have, or dolerites in the SWE 21 case, where it's erupted through crust and it's assimilated some crust. So you go from your typical basalt, which is quite low in silica, and you add silica to it, and we eventually stabilize orthoperoxene, but we make that orthoperoxene by dissolving olivine. We're also seeing the exact opposite in these dunite channels in Hartsbergite that we talked about from the mid-ocean ridges. So what's happening here is we have a Hartsbergite that is olivine plus orthoperoxene basically. We have a basalt passing through that's very low in silica. We're doing the opposite reaction. We're taking the orthoperoxene, we're reacting it with the liquid, and this should be 1 rather than 2, and we're making forsterite with a different composition of liquid. So we leave behind these dunite channels everywhere that these basalts have passed. All right. So this is just a big caveat, and I kind of mentioned it at the start, is when we're using these simplified diagrams, it looks like, you know, every single basalt here should end up at this eutectic, and we should only crystallize olivine, plagioclase, climperoxene. Or if we use this one, it looks like every basalt should end up hitting this peritectic at some point. But the problem here is these are simplified systems, so we're missing out on other components. So these are good for understanding concepts, and they're good for understanding these crystallization orders, and it was a really big tool kind of like earlier on in geochemistry to figure out like why things look the way they are. But they're not going to be fully representative of natural rocks. We will see basalts that crystallize more than olivine, climperoxene, and plagioclase. We will have basalts that never saturate in orthoperoxene. Okay, so just bear in mind that these are going to help us understand the concepts, but they're not like hard and fast rules for how magmas crystallize. Okay, I think that's everything I had. Yeah. All right. So I'll leave that up. Does anyone have any last questions on that bit? Yes, Bastian.
Yeah, I think I'm confused about the 3D peritectic.
Yeah.
You mentioned.
It's basically a 3D version of this.
Okay, but
So
there was anorthite.
Yep.
As well.
So the reaction has changed a bit, but we're still consuming olivine to make these two different minerals.
Yeah. So
Go ahead.
yeah. So if we move down and from the dew point and reach the instantite protective.
Yeah. Then we're reacting olivine with the liquid to make orthoperoxene, and the liquid composition is changing.
Okay, but is that a peritectic?
That's a peritectic. I don't know what the word would be for it. It's more of it's a boundary. But then here we're at a peritectic point. So again, because we've started to crystallize anorthite as well, we can only exist at one temperature. We've got 3 minerals plus melt, so we've got 0 degrees of freedom. So at this point, it will just sit at this temperature, dissolve olivine, and crystallize liquid to make andesitite and anorthite until all of it's gone.
Okay.
Yes.
If you have a starting melt in the andesite region and
Yeah.
you hit the eutectic point, would you then consume anorthite to produce forsterite?
No, because this is a eutectic point. So
no,
it's just
but
the,
if you started more or less over the, so you would hit the.
so I hit this
yes.
cotectic. So this is a cotectic, so it's not going to react in that way.
Okay, so
Yeah.
okay. So only forsterite can hit the
It
eutectic
definitely
point.
happens for other minerals, but of these, the only one that's a peritectic reaction is this conversion of olivine first into orthoperoxene and then into orthoperoxene and plagioclase. Yeah. Yeah.
What is
Norite, orthoperoxine and plagioclase. So it's like a gabbro, but if you replace the clinoproxene with orthoperoxine. Yeah. Okay, fantastic. I'll just leave these up for a second and we can take a break. Yeah. So should we say 5 minutes? Is that okay? 10 minutes? We'll say 5. We'll say, yeah.